Okay, our next speaker is William Toledo, which I'm taking he was part of the project. We heard the name. And he's going to discuss the bonding and doing a bonding assessment on that.
Good morning. My name is William Toledo, and today I'll be going over my work on the substrate influence on ultra-high performance concrete. Bond strain, sorry. Okay, so first off, I want to cover the objective of the study, which was to assess the effects of substrate surface preparation, specifically surface moisture condition and surface texture on non-proprietary ultra-high performance concrete overlay bond strength. Okay. So a little bit of background. So cementitious overlays, I guess we were familiar with them, but my work is mainly looking at bonding the UHPC to substrate concrete since we don't need a tack coat for this material. And in doing that, we need to look at cementitious overlays in general. So overlay systems is a popular deck repair strategy that can protect steel reinforcement by providing extra cover. So you can see in this, oh, you can't see my mouse. So you can see, no, you can't even see it here. That we provide extra cover there for the steel reinforcement. And it can extend service life of existing bridge decks and can be cost effective when compared to full deck reconstruction. And a little concrete bridge deck overlay is just a repair strategy, again, by providing a thin layer of repair concrete. And for UHPC, we're looking at maybe about 1 inch of depth. Okay, so going into some background regarding what types of stresses we're interested in or what can be cause for concern. And we see this thermal incompatibility between the substrate and overlay systems. And so this thermal compatibility can cause some stresses, and the differences in the thermal properties can provide this phenomenon called curling, where we have either upward curling or downward curling. Curling is just essentially we have a difference in moisture above the overlay and below the overlay. So it can be either temperature difference or moisture difference, okay? The extreme case or the worst case scenario would be upward curling where we get maximum shear stresses at the edges and maximum tensile stresses at the edges, okay? So background for ultra-high performance concrete, or UHPC, is what I'll be referring to. So UHPC is produced with fine materials, with the coarsest material being a fine sand that's passed through a number 4 sieve. It exhibits compressive strengths of at least 17,000 psi, has excellent durability against chemical and physical attacks. When tested for chloride ion permeability, showed extremely low, has little or no deterioration when exposed to 300 cycles of freezing and thawing, and showed very little mass loss when tested for abrasion resistance. And UHPC has excellent density and low porosity, excellent flexural strength, typically around 1,500 to 2,600 psi, and is ductile when fiber reinforced. Okay. And then, so typical composition for UHPC, or the typical composition for the non-proprietary UHPC we developed at New Mexico State University. So of course we have our, what we use is a type 1-2 cement, shown in the top left image there, photograph. And then we have our fine aggregates, which is again our fine sand that's passed through a number 4 sieve. And for ours, we oven dry it so it has essentially no moisture in it. And of course, we use our supplementary cementitious materials, starting out with the silica fume, which is the main ingredient for this mix. It's the main contributor to our early strength gain and main contributor to our bond development, because it's a nanoparticle that has the ability to infiltrate void spaces. Whatever void spaces are available in that substrate, it'll develop the bond there. And our other material is going to be a fly ash, which is a class F fly ash, and those two SCMs are going to be in the 2 middle photographs there, with the silica fume being the the darker material, and then the fly ash with the lighter material. Okay, and we have a low water to cementitious materials ratio, typically around 0.13 to about 0.16 is what we're looking at. And just to have that low of water to cementitious materials ratio, we need to implement a higher range water reducing admixture or a super plasticizer. And in this case, we're using the Master Delenium's 3030 or the 3030 mix super plasticizer, which is, you can see the container there in the bottom right photograph. And in order to have our ultra high performance, we need our high strength steel fibers. In this case, we're using needle fibers that is 13 millimeters long and has a length to diameter ratio of 65. Okay, so it's very fine material or fine fibers. Okay, now we're going to go into the experimental methods for this study. By first covering the concrete characterization. So we have two materials. This is going to be a laboratory testing. So we have our substrate material. That's going to be just a normal strength concrete. And then our overlay material is going to be, of course, the UHPC. So UHPC characterization, we wanted to look at workability. And this was assessed using the slump and flow test. Slump ran in accordance with ASTM C143. And flow ASTM C1611. We also need to assess compressive strength to make sure we do have UHPC with that 17,000 PSI requirement. We use the British standard for this, which use 4x4 cubes. And we also assessed the flexural strength on one of the mix, which was ran in accordance with ASTM C1609. And our substrate characterization, we just provided air content and a slump test, ran in accordance with ASTM C23 for that air content and ASTM C143 for that slump. And then we did do compressive strength testing, ran in accordance with ASTM C39. Okay, so now going into the actual bond assessment test. So here we provided, we call this slab specimens, but they're just small 6 by 6 by 24 inch beam specimens that has 4.5 inches of depth for that substrate concrete. And what we do is texture the top surface and then overlay that surface with a 1.5 inch thick UHPC overlay. Okay, so you can see that in the bottom left illustration. And so here's a in situ direct tension test. So we call this in situ just because we don't completely core out the specimen. So you can see in this right top image here, we core down into the specimen with the core saw bit that's about 1.875 inches in diameter. Core down about 2 inches, so 1.5 inches past the UHPC overlay and about 1/2 inch into the substrate concrete. And all we do is epoxy on steel load plan, as you see in the top right photograph, and then or illustration, and then you can see them down there in the bottom right photograph. We just epoxy that load platen on there, allow it to cure, and then use this fill pull-off tester to perform the direct tension pull-off test. And of course, this does provide a direct tension bond strength. Okay, so for this study, we're wanting to, I guess, describe the substrate surface preparation or what surface preparation we need. In doing so, we wanted to look at the substrate surface moisture condition as well as the substrate surface texture. So first off, we'll go over the surface textures that we use in this study. So we have 5 surface textures, with the first being shown in the first left image there, which is going to be that smooth texture, what we define as a smooth texture. So you do see some tines in there, but I guess, well, the tines don't really provide enough strength for bonding or developing direct tension strength. So what we're looking at mainly is that top surface, which is the smooth, or as we go into this other texturing. So we define the next textures as exposed aggregate. But more importantly than exposing aggregate is exposing that pore space of those aggregates. Okay, so, and we developed these, we defined these substrate surface textures. They're sandblasted textures, and they're defined by ACI 303's definition of these brush sandblast texture, which is the second image on the screen here. And that's it's partially exposing the fine aggregate of the substrate. And then we go into the light sandblasted texture, which exposes the fine aggregate, medium sandblasted texture, which partially exposes the coarse aggregate, and then our roughest texture is going to be our heavy sandblasted, which exposes coarse aggregate. Okay, so you can see those in the bottom images here. And then now going into the substrate surface moisture conditions. So first off, we wanted to look at surface conditions from saturated all the way to dry case, right? So with the image on the left here, this is our saturated case, so you can see some freestanding moisture and water on the surface. And we call this the zero minute dry time just because we maintain saturation up until application of that UHPC overlay. And then the other moisture conditions is we just allow it to dry. And of course, these the time aspect is really independent or dependent on where the location is. And here we're looking at a laboratory which has a 68 degrees Fahrenheit and 30% relative humidity. So that's just descriptive as to for these photographs. So okay, so going to from 0 minutes, of course, we're maintaining moisture, and then 15 minutes we're allowed to dry for 15 minutes, and then going on 30 minutes, and then 45 minutes would be what we define as a saturated surface dry. This is the last case where there's visible moisture on that surface. And then we go into our dry cases where we're allowed to dry for 1 hour or 60 minutes, and that's figure E here. And then our what we define as dry is going to be dried for 2 hours and shown in figure F. Okay. Okay, so now we're going to talk about 3 parts of this study, with the first part being where we want to investigate the 2 extreme aspects. We want to look at the saturated condition as well as the dry condition, okay? So, and then with the dry specimens, we had a smooth or heavy sandblasted surface texture, and the saturated specimens, we had smooth, light sandblasted, or a medium sandblasted surface texture. And after we assess the extreme cases, we want to look at in between dry and saturated. So we did a partially dried substrate surface moisture condition, and and then this is where we implemented the timing, and this is where we did the 15, 30, 45, and 60 minutes, with that 45-minute being that last case where there's visible moisture on the surface. And then the last study was the surface texture, and specifically a surface texture that provided a degree of aggregate exposure. This is where we implemented the ACI 303's definition of those sandblasted textures, which has a varying degree of exposed aggregate surface textures. And then one thing to note for the partially dry substrate surface texture is that this study we're using the light sandblasted textures, and then the surface texture study we're using the 45-minute dry case, where we had the last, which is the figure D here, where it's the last case where we have visible moisture on the surface. Okay. Now we're going into the results from this study, starting off with the concrete characterization. And with the concrete characterization, we're starting off with the UHPC. So our UHPC mix is a thixotropic UHPC mixture. Thixotropic just means it's very viscous at rest and won't move until energy is put in to move it. So we wanted a thixotropic mixture just because we have no control on where we're placing this overlay system. If we place it on a sloped surface, we don't want it running off and accumulating at the bottom. We want it to sit still until energy is put in to move it with the vibrating screed or vibrating needle. So we have 2 mixtures of 2 UHPC mixtures here, with the first one being We replaced 20% of our cement with supplementary cementitious materials that's made up of a 50% blend of silica fume and fly ash, so those they'll have the same number there for their mass. And for this mixture, we had a 0.15 water to cementitious materials ratio, and we used 1.5% of steel fibers. And UHPC2, we have we're taking out 20% of our cement, replacing it with, in this case, we're using the 62.5% of silica fume, 37.5% of our fly ash. And for this one, our water to cementitious materials ratio is going to be 0.145, and our steel fiber content is going to be 1.75%. So we picked these mixtures, or we select these mixtures because they provide adequate workability, with the UHC1 having a slump of 6 inches and a flow of 10 inches. Oh, sorry. Yeah. And UHPC2 having a 5 1/4 inch slump and a flow of 9 3/4. And of course, we needed to meet that ASTM-C 1856 compressive strength of 17,000 PSI at 28 days, which we did with both UHPC mixtures, UHPC1 having 17,590 PSI, and UHPC2 having 17,270 PSI at 28 days. And we also did exceeded the minimum Federal Highway Administration flexural strength of 900 PSI for that UHPC1, having a flexural strength of 1,490 PSI. Okay. Now going on to the substrate concrete characterization. So this mix, the substrate concrete had a 0.4 water to cement ratio, and it was designed to have a slump of 2 to 3 inches and air content of 5%. And the 28-day compressive strength was 6,600 PSI, and you can see here from the mixture proportions that it was an air-entrained concrete. Okay. Now going into the actual results for the bond assessment test, starting off with the surface moisture conditions. So a little bit about this plot here. So you see two lines, a dotted line and a solid line. So the dotted line is going to be ACI 546 recommendation for a good bond strength of 150 PSI. And that solid black line is ACI 546 excellent, recommendation for excellent bond strength of 250 PSI. So you can see specimens that were dried for 15 to 30 minutes. Again, just a refresher, a 15 and 30 minute dry case it's not saturated, or it doesn't have a lot of visible free moisture on the surface. It's just in between these 0 minute and 45 minutes. So saturated surface dry conditions and saturated. So for those two, we were able to exceed that 250 PSI excellent bond strength recommendation. And you can see all cases that had visible moisture, that's 45-minute dry time or less, were able to exceed that 150 PSI good bond strength. And you can see that when we allowed the specimens to dry for more than 45 minutes, for 60-minute or 2 hours, we did not develop any bond strength. And one thing to note from this is that 2 hours dried specimen is going to be an exposed aggregate texture, or the heavy sandblasted texture. So this is the ideal case, having an exposed aggregate, an exposed pore space for that develop bond. But by not having that water present, it didn't allow the development of a bond, because we need that water to essentially provide an avenue for that silica fume to infiltrate these pore spaces, right? So if we don't have that freestanding water on the surface, or any moisture on the surface, we're not going to get that bond development. Okay. And then here we have the surface texture study. Same thing, we have our ACI 546 good bond strength of 150 PSI, denoted with the dotted line, and the ACI 546 excellent bond strength of a 250 PSI, denoted with a solid black line. Okay, so we can see by providing surface textures, or exposed aggregate textures, degrees of exposed aggregate, we get more bond strength. And with the ACI or the medium and heavy sandblasted textures were exceeding that 250 psi. And one thing you need to note is that the smooth case, again, the smooth case is we didn't remove any of that surface space. And so the smooth case is a saturated it's at saturated conditions, okay? So that means it's the ideal case. We have saturated surface, we're not dry. However, by not removing any of that surface space and exposing any aggregates, we don't develop, we don't develop good bond. We do develop bond, but it's less than 150 psi on average. And by exposing more aggregate, we get more bond strength. So essentially, from these two studies, we need two things, right? We need moisture on the surface. Well, we need to see, we have to actually see, like have visible moisture on the surface. And we also need to expose aggregate. And just by removing a little bit of surface space and exposing, partially exposing fine aggregate, we're able to develop that 150 psi bond strength, which is good. Okay, so conclusions from the study. UHPC overlays placed on visibly dry substrates eliminated drastic consequences of maintaining adequate moisture. So that was shown here where by drying it more than those 45-minute dry time, we're not developing any bond. And then adequate bond strengths greater than 150 psi at 7 days were achieved on any degree of aggregate exposure when we had essentially a moist surface on that for that substrate surface. Textures were with increasing amounts of aggregate exposure, and that was just from this one here. As we expose more aggregate, we get more surface texture. Or sorry, we get more surface. Bond strength. So excess moisture. So this is where we had excess moisture on the surface that it didn't provide as much bond as these other cases where the 15-minute, 30 minutes we were exceeding that 250 psi, whereas the saturated conditions where we had freestanding moisture, we did exceed the 150 psi, but we weren't able to get to that 250 psi recommendation. And then we saw that slightly inadequate bond strengths were observed for specimens that had a thin layer of free moisture, and that's the saturated case. But by not providing any exposed aggregate texturing, we weren't able to get adequate bond strengths for those specimens, even though we had that saturated condition. Okay. Some acknowledgements for this study. So, of course, Transset for funding the project, BASF Chemical Company for the donations of silica fume and admixtures, the Salt River Materials Group for their donations of fly ash, and NMDOT for their continued support and collaboration. Okay. All right, thank you.
Do we have any questions?
So, quick question. Because you cored through the UHPC and you were doing bond tests, was it the substrate that failed or did the UHPC fail?
Many of the tests are substrate failure. So the substrate failure, it's very conservative just because it's we make the substrate in labs, so they're going to be at essentially 14 days of strength. So any failure is going to be a conservative failure. Okay, so you're saying you would only characterize bond as if it has bond failure? I think I would disagree just because the bond's withstanding that failure, right? So we're breaking at the substrate, and then, so it's essentially more than that. Yeah.
You listed drying times. How long did it take to achieve a saturated condition? How long were you exposing the substrate to moisture prior to your starting the clock?
So we just maintain moisture. So as we're mixing the UHPC, we're just constantly providing moisture on that surface and keeping it at that saturated condition. Good.
Okay.
Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.